Hi, welcome to this video on time-traveling simulators using blockchains and their applications. I'm Pratik Soni from Carnegie Mellon University, and this is joint work with Vipul Goyal and Justin Raizes. So in this work, we introduce a new way to capture security for cryptographic systems using blockchains. So blockchain is an emerging new technology where a set of computers distributed over the internet, they come together to maintain a global public ledger. And this ledger provides several interesting properties. For example, it's an append-only ledger, so data can only be added to the ledger but not removed. Anybody on the internet can add data to this ledger. Anybody with an internet access can get the latest state of the blockchain. Most importantly, all honest parties have the same view of the ledger. The central application of blockchains has been to get decentralized cryptocurrencies like Ethereum and Bitcoin, which today have a combined market value of 1 trillion US dollars. But now blockchains have infiltrated many different areas and have several different applications. Blockchains have often been viewed as a consumer of cryptography, and in fact, designing cryptography for blockchains is a rapidly advancing and a well-motivated research direction. But recently, blockchains are also being viewed as an enabler for cryptography. And there are several interesting properties of blockchains that make them suitable for building cryptography. For example, the work of Goyal and Goyal use blockchains as an alternative to trusted setups to build non-interactive zero-knowledge. A sequence of works use blockchains to achieve fairness in multi-party computation. And quite interestingly, blockchains enable encrypting to the future via this notion of time lock encryption. In this work, we want to take this direction even further and ask a meta-level question. Specifically, we ask whether blockchains can enable us to capture new interesting security properties. We here seek for a new security definition. But how do we prove security in cryptography to begin with? So a common goal in cryptography is to quantify the knowledge an adversary learns when it's interacting with a crypto system. So consider the example in the slide, where an adversary is interacting with Alice, she's in possession of some secret, and the adversary is actively trying to learn some information about the secret. For security, we would like to show that the adversary learns no information about the secret from this interaction. This is typically argued by showing the existence of a simulator who can simulate the adversary's interaction with Alice without having access to Alice's secret. And this intuitively implies that the adversary learns no non-trivial information about the secret. This simulation paradigm is central to proving security of a number of crypto systems, including encryption schemes, zero-knowledge proofs, multi-party computation, program obfuscation. So adversary paradigm is prevalent throughout cryptography. Ideally, we would like to have simulator and the adversary have the same powers. But for feasibility, simulator is often given extra power over the adversary. And this extra power over the adversary manifests itself in many different ways. For example, the simulator is allowed to rewind the adversary, is allowed sometimes given access to the code of the adversary, or even allowed to run in time significantly larger than the adversary. And all of these different powers give rise to different security notions. In this work, we give a new power to the simulator, the power of time travel. We give the simulator a peek into the future. Specifically, we give the simulator a future blockchain state. We refer to such a simulator as a time-traveling simulator and the corresponding notion as time travel simulation. The primary contribution of our work is to rigorously define this notion of time-traveling simulation using the idea of blockchains. And hopefully, as we will see later in the talk, that time-traveling simulation is non-trivial, gives interesting security guarantees, and is oftentimes easier to work with. Additionally, we also investigate the power of time-traveling simulation in the context of two fundamental cryptographic tasks of zero-knowledge proofs and secure-to-party computation. Specifically, in each of these situations, we give a 3-round protocol. Specifically, we give a 3-round protocol for zero-knowledge, where the zero-knowledge is defined with respect to a time-traveling black box simulator. We also show a 3-round secure two-party computation where we get time-traveling simulation security against both parties. These 3-round protocols highlight the usefulness of our new notion. Specifically, 3-round protocols with standard simulation were either impossible or required novel assumptions in the context of zero knowledge, whereas no construction for 3-round two-party computation was known prior to our work for polynomial time simulation. So in the rest of the talk is divided into 4 parts. In the first part, I want to give you a quick overview of blockchains, and this will set us up nicely to define our new notion of time-traveling simulation in the context of zero knowledge for interactive proofs. Then we will state our results a bit more formally. And finally, in part 4, I'll briefly describe our 3-round zero knowledge construction, which will hopefully give you a taste of how time-traveling simulation is used. So blockchains. So in blockchains, there are users who want to post data, and then there are a set of miners who are running a distributed consensus protocol to maintain the ledger. Specifically, users who want to post some data, they send it to this network of miners, whereupon one of these miners is chosen as the leader according to the rules of the underlying consensus protocol, and then this leader gets to append this data in the form of blocks to the ledger. And blockchain continuously grow. Users can post more data, a new leader is elected, and new blocks get added to the chain. A little bit more detail, these blocks not only contain data, but also contain a pointer to the previous block. And this is what results in the formation of a block chain. And these pointers are particularly useful because they enable us to check whether two blocks are adjacent or not. Specifically, there is this isValid predicate, which can checks returns 1 if you give the isValid predicate 2 adjacent blocks. Specifically, the isValid predicate on blocks A and B is going to return 1, but on A and C is going to return 0. And this is particularly useful when someone with the candidate block D can check whether it's a valid extension of the current blockchain state C or not. But how are new blocks getting generated? Recall, leader is the one who gets to add new blocks to the chain. So miners are continuously engaged in a puzzle solving race where they are solving moderately hard puzzles, and the winner of this race becomes the leader. The puzzle solving race is simulated in many different ways, but the key idea is to ensure that the probability of getting elected as a leader is proportional to the resources that the miner devotes to the system. The earliest of the blockchains, like Bitcoin, were based on a proof of work based mechanism where miners are continually devoting their CPU cycles to solve some puzzles, and the probability of getting selected as the leader is proportional to their computing power. But now several other interesting proposals are in place, like proof of stake, proof of space time, and so on. The key idea behind all of these proposals is just to prevent the notorious Sybil attacks, which are well known in the literature. A main assumption underlying all of these blockchains is the honest majority assumption, where irrespective of which of these resources are used or which of these mechanisms are used as the puzzle solving race, we want to ensure that the adversary does not control more than 50% of the computing power. And this is referred to as the honest majority assumption, and this is what enables interesting properties like consensus. And this is also going to be relevant for us later in the talk. Okay, so now that we have defined, now that we have described what blockchains are, let me now define this notion of time-traveling simulation for zero knowledge. Okay, so what are interactive proofs? Interactive proofs are an interactive protocol between two parties, prover and the verifier, where the prover is trying to prove to the verifier that a certain statement X is true. And we want standard properties like completeness, which says that if the statement is indeed true or it belongs to this language, then the honest prover can convince the verifier. We also want Soundness, which says that if the statement is indeed false, then no cheating prover should be able to convince the verifier to accept. The most relevant security property for today's talk is zero knowledge, which provides privacy guarantees against a cheating verifier. Specifically, we say an interactive proof system is zero knowledge if the cheating verifier learns no information about the prover's witness from the interaction. Recall from the interaction that this is argued by showing the existence of a simulator that can simulate the view of the verifier with the prover without knowing the prover's witness. And this is a seminal notion introduced in the work of Goldwasser, McCauley, and Rakoff in '89, and they require the simulator to run in polynomial time. So the philosophy, we refer to this notion introduced by GMR as the standard notion of zero knowledge. And really the philosophy behind the standard notion of zero knowledge is that whatever the verifier learns from interacting with the prover, it could have computed on its own by running the simulator, which runs in polynomial time. And there have been numerous other formulations since the seminal work of Goldwasser, McCauley, and Rakoff that capture different philosophies. For example, there's this notion called zero knowledge in the CRS model, where which enables the following guarantee that whatever the verifier learns from the proof, it could have computed on its own if it had access to the trapdoors inside the CRS. And since and here the simulator is given access, or rather the ability to sample the CRS trapdoor. So in this work, we focus on achieving a very different philosophy, right? So we want to achieve that whatever the verifier learns from the proof, it could have computed on its own shortly into the future. And to capture this, we have to give simulator the ability to look into the future. And we call the resulting notion as time traveling zero knowledge. And really the question is, how do we formalize this? Because this requires a notion of time, right? And this is where blockchains are particularly useful because they give us a natural notion of time. For example, the blocks being continuously added can be used as a parameter for keeping track of time. So before I can define the time traveling simulation formally, we'll have to adapt our protocol to the presence of blockchain. For example, the current state of the blockchain is now going to be given as common input to all parties, including the prover, the verifier, the adversary, and as well as the simulator. Additionally, the simulator will be given an extra input, which is an F block valid extension of the current state of the blockchain. And as we will see later in the talk, that this is particularly useful because such an F block extension cannot be computed by an adversary that controls only minority computing power. And this is what would allow us to show soundness of our proof systems. But for now, let's go back to formally define this notion of time traveling zero knowledge. So recall now that all parties are given ST, which is the current state of the blockchain, in addition to their regular inputs. And additionally, simulator is now given this additional input of B1 through BF, which is an F block valid extension of the current state of the blockchain, right? And we call a proof system to satisfy F time traveling zero knowledge if there is a simulator that works for all cheating verifiers. By works we mean that they are able to simulate the view of all verifiers. Now, I've given you this new notion. You need to ask me how interesting or how good is this time traveling simulation, right? Really, at the very core, what it tries to capture is that the only information that the verifier learns from interacting with the prover today, it would have anyways learned tomorrow, for example, after F blocks are being added. And this already seems a little bit weaker than the standard notion of zero knowledge, and technically it is, but really the differences depend on the statement that you're proving. To substantiate my point, let's consider a couple of examples. So for example, if you are using a proof system a zero knowledge proof system to prove statements of the form where the statement is a commitment to honest party's input and randomness, and the witness is the honest party's input and randomness, then really the time traveling notion of zero knowledge gives essentially the same guarantees as the standard notion of zero knowledge. This is because passage of time or adding more blocks to the blockchain is not going to magically break the security of the commitment schemes. So really, the only information that the verifier would learn from the addition of new blocks to the blockchain would be independent of the corresponding statement that we're proving. Having said that, really, if you're using time traveling simulation proof systems for proving statements of the form which includes a time lock puzzle whose solution is inherently going to be, let's say, for example, leak tomorrow, then the time traveling simulation zero knowledge proof systems would end up leaking the solution today itself. So in this sense, it's weaker than the standard notion of zero knowledge. Also, we are not the first one to give additional powers to the simulator. For example, there is this well-studied line of work which is called a super polynomial simulation, wherein the simulator is given access to a super powerful oracle or an angel that breaks, for example, commitments of certain security of certain commitment schemes. Although this is as a notion, it's very impactful and allows us to circumvent numerous impossibility results. Really, there's a big drawback of this notion is that it's very hard to argue the security of the honest parties in the presence of such a powerful angel. So, in summary, this results in more complicated proofs for super polynomial time simulation. Time traveling simulation can also be viewed as a super polynomial time simulation where the angel is provides a specific functionality. Specifically, it gives it computes the future blockchain states and provides them instantaneously to you. However, an advantage in our scheme is that really the security that the angel breaks is not that it's breaking a commitment scheme, but rather something that would automatically be broken in the future. Right, so this gives us this tells us that the time traveling simulation zero knowledge is certainly stronger than super polynomial simulation, and it's easier to understand and results in simpler proofs, simpler security proofs. So zero knowledge simulation has also been considered previously in the blockchain model. For example, there is this line of work by Chaudhary, Goyal, and Jain, where they introduced this new notion of standard simulation in the context of in the presence of blockchain. However, this notion was shown to be impossible for constant round protocols. Comparatively, our notion is actually, as we show, is indeed possible to achieve for 3-round protocols. And arguably with a very simple construction, hopefully, that we will see at the end of the talk. I also want to mention another notion called the majority notion, considered by the work of Goyal and Goyal. In fact, this is possible to achieve also for non-interactive protocols, but here the simulator is given a lot of power. Specifically, it controls all honest parties in the blockchain network. For example, this can allow the simulator to pause the blockchain and even rewind and delete blocks from the blockchain, right? Comparatively, in the time traveling simulation setting, the simulator only controls one party, and having access to, for example, having access to this future state doesn't let the simulator go back and rewind the blockchain, for example. Okay, so hopefully by this point you're familiar with the notion of time traveling simulation zero knowledge and see how it compares to many different notions proposed in the literature. And now this has set us up to say our results a bit more formally. So the first theorem that we show is that assuming the existence of injective one-way functions, we show that there is a 3-round zero knowledge argument where the zero knowledge is with respect to a strict polynomial time black box time traveling simulator. And comparatively, achieving the same task using standard simulation is known to be impossible for black box simulation, and for non-black box simulation, even though constructions are known, they require novel cryptographic assumptions. So I want to say a little bit more that like the zero knowledge aspect of our construction follows directly from one-way functions. Soundness, however, requires making new but natural assumptions on the underlying mining puzzles. Although Theorem does not say this explicitly, at a very intuitive level, what we want is that, let's say, a group of miners and the adversary who controls minority computational power, they start creating blocks. They start creating extensions from a specific block, let's say A. Then the adversary cannot outpace the honest miners, and this seems a very natural assumption to make. However, in the paper, we need more natural strengthenings of this assumption for our constructions. I also want to quickly mention about our two-party secure computation results. So two-party computation is a protocol between two parties, let's say Alice and Bob, who have their private inputs X and Y, and they want to jointly compute the function, some function F. Here we want the correctness guarantee that the receiver, which is basically this party, always gets the output f of x comma y. And in terms of simulation, securities is defined via the notion of a simulation, wherein we want to capture that each of the parties do not learn anything about the other party's input, right? Although I've not defined explicitly, but time-traveling simulation can also be extended to the setting of two-party computation, which we define in the paper. We actually give our theorem more concretely is assuming the existence of injective one-way functions and public key encryption and signatures and two-round oblivious transfer, we build a three-round two-party secure computation protocol wherein we achieve simulation security against both parties, and the simulation security is with respect to a time-traveling simulator. So prior work on building three-round two-party computation protocols for standard simulation was only known for a weaker class of adversaries. Okay, so in the final few minutes, I want to give you a taste of how the construction of our three-round zero knowledge protocol. So our three-round construction follows the Feige-Shamir-Lapidot paradigm, where the prover is given the prover and the verifier are given a common blockchain state ST, and also the prover now wants to prove to the verifier that X is in the language. To do so, the prover actually gives out a witness indistinguishable proof, showing it either knows a witness for X or knows some trapdoor. And this trapdoor information in our case is going to be a F block valid extension of the current blockchain state. Note that the honest prover can actually produce a proof for the witness indistinguishable proof using the real witness W. The simulator is quite straightforward. The simulator is given access to an F block extension and hence can compute the witness indistinguishable proof and accepting witness indistinguishable proof using the second branch in the language. And by witness indistinguishability of the underlying proof system, it's straightforward to see that the simulator does a good job in simulating the view of the verifier. So really, the construction is simple. The time-traveling zero-knowledge security guarantee is pretty much straightforward, but really soundness is where we have to start working a bit harder. Specifically, we want to show that no cheating prover can convince the verifier on some statement X that is not in the language. Intuitively, we want to argue that for such statements not in the language, it's not possible for the prover to use the trapdoor branch or the branch B2 or for the witness indistinguishable proof system. But there's an issue here. The adversary could actually just wait until F blocks are added to the current state of the blockchain, and this allows the prover to get the witness to prove the trapdoor branch. Right? So to resolve this, we have to implement a timeout mechanism. Let's say we introduce a timeout parameter k, which is much less than F, and the verifier starts rejecting proofs from the prover if indeed it takes a long time for the prover to produce the proof. And of course, we have to we set k appropriately so that the honest prover doesn't actually time out. Okay. So really now to show soundness, we want to leverage the fact that the underlying witness indistinguishable proof system has a special property called special soundness. Specifically, for every input, for every string x, if the adversary gives out, let's say, two witness indistinguishable proofs, accepting proofs, where the first statement, where the first message remains the same, then the witness indistinguishable proof's special soundness property provides a way to extract a witness w prime, which is either a witness for the language for x or a valid f block extension. And this also holds for x not in the language. And in that case, the special soundness of the underlying WI system provides us a way to extract an f block extension. Okay? And this is going to be the key idea behind the soundness proof. Specifically, we want to use the cheating prover that gives convincing proofs for false statements and extract a valid f block extension from such an adversary. But the challenge here is that the honest prover, the cheating prover ends up interacting with the blockchain. This means that the blockchain adversary that we are trying to build needs to be able to simulate the blockchain in each of these threads, thread 1 and thread prime, 1 prime for the adversary. The way we solve this is by allowing the adversary enough power to compute short forks. At a very, very high level, this is how the reduction or how we would build the blockchain adversary. So the blockchain adversary, let's say, is given the current state of the blockchain ST. It internally runs the cheating prover, waits for it to reply with the first message, W1, and let's say the blockchain has expanded its state to ST1 by that time. At this point, the simulator, the blockchain adversary internally creates a fork of the current blockchain state, denoted by orange in the slides, and continues the execution of thread 1 and thread 1 prime with the adversary. Note that in thread 1, it is still interacting with the global blockchain, but in thread 1 prime, it's interacting with the local blockchain that the blockchain adversary is internally trying to compute. And most importantly, note that since the cheating prover will time out within k blocks are being added, the blockchain adversary only needs to create a small fork of k blocks internally. And now, given two transcripts, thread 1 and thread prime, we should be able to extract an f block extension of the current blockchain state. And this clearly violates or implicitly violates an assumption on the hardness of the mining procedure. At a very informal level, what we really want is that an adversary who's given an ability to create a fork of k blocks at maybe the rate proportional to that of the honest miners is somehow magically cannot produce a chain of f blocks where f is substantially larger than k. This is a very informal description of the assumption that we need. For more formal version, we outline in the paper. Okay, finally, towards conclusion. So in this work, we introduced this new notion of zero-knowledge new notion of simulator called time-traveling simulator. We define this rigorously using blockchains, and we also investigate the power of these time-traveling simulators in the context of zero-knowledge and secure 2PC. Okay, so I couldn't cover a lot of details, and I invite you to look at the paper. But at a very high level, we have to work harder to adapt to blockchain's weak consensus. Note that today we implicitly assume that all honest parties agree on the current blockchain state, but rather blockchain provide you only with a weaker guarantee that all honest parties agree on all but the final few blocks. So adapting to this weak consensus requires a bit of work. In the context of our zero-knowledge protocol, what the property that turns out to be more useful is a strengthening of the soundness called argument of knowledge, which we didn't discuss today. So in the paper, we have to formulate a new notion of argument of knowledge with respect to a time-traveling knowledge extractor. For our 3-round 2PC result, the key component is a way to extract adversaries' inputs For this, we have to come up with a new two-round protocol for an extractable commitment scheme where the extractor also is a time-traveling extractor. And finally, our current techniques only work with proof-of-work-based blockchains. Would be interesting to extend this to other blockchains. Specifically, the issue is that for our constructions, we still require that having an adversary that has access to all the secret keys of the honest miners can still not outpace the honest miners in computing the blocks. And this is true for proof of work based blockchains, but certainly not true for proof of stake based blockchains. So there's a lot more interesting questions arising out of this work that I hope you guys look at and solve. So thank you for listening. The paper is on ePrint. Thanks again.